This is CPE 133. This is Chapter 13 in the Free Range Verilog Foundation Modeling text. This is a continued discussion of modeling finite state machines using Verilog, which we refer to as behavioral modeling. So the best way to learn Verilog is just actually grind out some circuits, solve some problems. Watching videos, reading the book helps, but you actually need to do it to learn it. By all means, go out, do it, learn it, ask good questions, make good mistakes. So a bit of review here. Basically, essentially finite state machines are circuits that control other circuits, and typically we're talking about digital circuits here, of course. And it's a very classically, it comes at the end of your digital design course, and it allows you to design some really interesting circuit. Now the issue here is that circuit design using a state machine requires two things. One, you got to design the circuit. Two, you got to design the state machine that controls the circuit. And the way we're going to design that state machine is essentially with a state diagram. So the approach we're taking to model finite state machines in this chapter is relatively high, which is why we call it behavioral modeling. So essentially we're describing the behavior of the state machine, and we're not giving too much of a care about the low-level details. So this is our old model. This is our old model here. This is our standard state machine model up here, and what we've done is we've kind of redesigned it for our behavioral modeling. Essentially, there's two decoders in this circuit here. We've combined them into one combinatorial circuit in our Verilog behavioral model. And so the issue here is the combinatorial circuit handles two things. It handles the assignment of the next state, but it also handles the assignment of the outputs, determines what the outputs are. The sequential circuit here handles two things. Essentially, it's a state registers, of course, but also it handles the asynchronous inputs. The other external inputs that are not asynchronous become part of the combinatorial circuit. So this is our example problem. What we want to do is model this state diagram using Verilog behavioral modeling. First step is just to look at this and particularly just kind of understand what's going on, and maybe get an idea for circuits inputs and outputs and what's synchronous and asynchronous. When we look at this thing, it does have four states. Yeah, that's pretty obvious. There's no asynchronous inputs, so that's okay. Outputs, it looks like we have just an output of count, which is 2 bits. What else do we have there? As far as inputs go, it looks like we have one input, which is RST, certainly not asynchronous input. This problem actually calls out the count values here. So this looks kind of like a counter, because you can see 1, 2, 3, 0, and the states are named properly. So a lot of information in this. We're ready to crank through this thing. So this is our interface right here. It says the same thing. This is saying right here in the top of the module. So that's our interface, that's our start. Next thing we want to do is encode those states. So we see there's 4 states, so we need at least 2 bits here. There are our 2 bits. There are 2 variables are going to be the present state and next state. And I've actually called out these state names. These are just simply constants, but they're constants that I can assign values. And so both the name and the value is important. That's kind of preliminary work. This is the entire sequential process. When there's a clock edge, positive clock edge, it's going to assign the next state to the present state, which is going to allow the circuit to actually do a counting operation. So if you look at this circuit, you can see that when reset is a 0, it actually resets this counter by directing all the states back to state 0. Any other times when RST is not asserted, which was RST is a 1, like it's a reset, it's going to do normal counting. You can see that normal counting come around the back like this. So, and when it hits the 3 state, it's always going to transition back to the 0 state. It doesn't matter whether it's reset is pressed or not. Even if reset isn't pressed, it still goes back to the 0 state, which is why we have a don't care there. So this is the always block describing the combinatorial circuit. And so what I'm responsible to do in this is just generate the more output. Now, if you notice, if you look at this thing, it does not have any mealy outputs. So when I'm in state 0, and here's state 0 right here, the reset needs to be part of that state. It's not asynchronous, and so we're going to see it up there, and we can see 2 arrows leaving. Basically, the value of the reset signal determines where it's going to transition to. So if reset's a 0, it goes back to state 0, and you can see it right there. Otherwise, reset's a 1, it allows it to count, and it goes to the next state. Now this is very similar to the second state, but you can see the reset still goes back to 0, but 1 goes to 2. The counts in all these states are more outputs, and they're encoded as more outputs. And so I made these smaller so you can barely read them, but the issue here is it does have a default. I like seeing defaults in here, and I just assigned it a next state of 0 just to put something there. The issue in this problem is that there's 4 variables, 4 different possibilities for the 2 state registers. I provided a case statement for each, so I could actually get away without this default, but I still think it's a good idea to put it in there. It may generate a warning, but hey, it's just a warning. So in summary, finite state machines, they're circuits that control other circuits. The best way to describe finite state machines with a state diagram. So Verilog behavioral model, essentially it's a high level way of modeling state diagrams. It's super simple, kind of cookbook when you start from a state diagram. The way we're modeling it, once again, it breaks the next state decoder and the output decoder into one combinatorial process and also one sequential process that handles the state registers.